Hello everyone, I'm Kazuhiro Kurita from Japan. Today I will talk about efficient enumeration for multicuts and multiway cuts. This is a joint work with Yasaki Kobayashi. Let's start. First, the minimum ST cut problem and the minimum ST separator problems are well-known classical problems. Their problems can be solved in polynomial time. As a natural extension of these problems, there are the edge or node multicut and multiway cut problems. In this problem, we give a set of pair of vertices called terminal pair. In this problem, we find a set of edges or vertices with a minimum cardinality which breaks all connectivity of terminal pairs. In the optimization algorithm area, these problems are widely studied and there are many hardness results and positive results. However, enumeration of node or edge multiway cut or multicuts have not been well studied. In our paper, we propose 3 efficient enumeration algorithms and prove one hardest result. Okay, we give the definition of multicut and multiway cut. Let P be a set of pair of vertices. A set of vertices M is called a node multicut of G and B if any pair of vertices in B is not connected in G minus M. Here, a vertex B is called terminal if B is contained in a pair of vertices in B. Moreover, a set of vertices in B is denoted by T of B, and we call a vertex in T of B as a terminal. Next, a node or edge multiway cut M is special case of node or edge multicut. In multiway cut, B is contained in U and B and W. Then B contains a pair of vertices U and W. Moreover, M is called minimal if any subset of M is not multicut and multiway cuts. Please look at this figure. This is a concrete example of a minimal node multicut. In this figure, we disconnect any pair of vertices in B. And in this figure, any terminal pair are disconnected. Finally, by removing these dotted edges, we can disconnect all pair of terminals. Next, we define our problems. The minimal node multicut enumeration problem. An input is a graph G and terminal pair B. Task is output or minimal node multicut of G and B. The next problems are the minimal edge or node multiway cut enumeration problems. An input is graph G and a set of terminals T. A task is the output or minimal edge or node multiway cuts. The bottom of the figures are example of node multicut and node multiway cut and an edge multiway cut. Next, we will explain how to evaluate the efficiency of enumeration algorithms. In enumeration algorithm area, we evaluate the efficiency of our algorithm by the measure called the delay. The delay of enumeration algorithm is the maximum time for each pair of consecutive two solutions. An enumeration algorithm is called a polynomial delay if the delay of this algorithm is bounded by a polynomial of the size of an input. Moreover, an enumeration algorithm code is an incremental polynomial. If to output I solution, the algorithm needs a polynomial of n plus I time, where n is the size of an input. Multicut and multiway cut have been received some previous work in the field of enumeration and optimization. In the context of optimization, it is known that minimum ST-cat separator can be solved in polynomial time. This is a special case of minimum edge or node multicut. If the number of terminals is exactly 2, then these problems are same. Moreover, if the number of terminals are more than 2, then this problem is NP-hard, even if graph is planar. Next, it is known that fixed parameterized tractability and approximation algorithms. And minimum node multiway cut is FPT parameterized by the solution size. On the other hand, minimum node multicut is W1 hard parameterized by the solution size. As a result of an approximation algorithm, a minimum multicut can be solved with 1.5 minus 1 over k approximation factor, where k is the size of solution. Finally, as a result of enumeration, an incremental polynomial time enumeration algorithm for multicut is known. Moreover, Minimal ST-cut separator can be solved in polynomial delay. In our result, we propose 3 efficient enumeration algorithms and prove one hardness result. In the previous result, we need an incremental polynomial time and exponential space for enumerating edge Multiway cuts. In our result, this problem can be solved in polynomial delay and polynomial stage. Moreover, we propose an incremental polynomial algorithm for node merge cuts and polynomial delay algorithm for node Multiway cuts. These algorithms need exponential space. Finally, we show the hardness result for enumeration of Steiner node merge cut enumeration. This problem is harder than enumeration of minimal transversals. Efficient enumeration of minimal transversals are a long-standing open problem in enumeration algorithm area. Next, we explain our algorithms. First, we explain a basic technique to design our algorithms. Our algorithms are based on the supergraph technique. In this technique, we construct a directed graph. Each vertex in the directed graph corresponds to a solution. To define the neighbor of each solution, we design an algorithm which outputs different solutions based on one solution. In this figure, we consider a node merge cut enumeration problem. We can find one minimal solution easily. Using this solution, we can generate other solutions like this. First, we have this solution, and we generate these solutions. By applying this algorithm recursively, we obtain many solutions. Next, we consider how to prove that output contains all solutions. To ensure that we can enumerate all solutions, our strategy is ensuring the directed graph is strongly connected. If it is true, then we can traverse all vertices in the supergraph starting from arbitrary solution. So the following algorithms, our aim is to prove that the supergraph is strongly connected. To prove the strong connectivity, we use the distance function. The function takes a pair of solutions and return an integer. Moreover, this function satisfies the follows. This S1, S2 is equal to 0 if and only if S1 equals S2. We call the value of this S1, S2 the distance from S1 to S2. We consider how to prove the strong connectivity using this function. We consider this observation. For any pair of solution S1 and S2, if S1 has a neighbor S3 which satisfies this S1, S3 and S2 less than this S1 and S2, then a supergraph is strongly connected. Thus, to prove the correctness of enumeration algorithms, it is enough to develop a distance function and neighbors which satisfy the above conditions. So, in our algorithm, we prove these conditions. We explain the detail of our algorithms. We first explain an incremental polynomial time enumeration of minimal node merge cuts. We first consider the characterization of minimal node merge cuts. This characterization is used for define the distance function. A set of vertices M is minimal node merge cut if and only if a graph G minus M has connected component C1 to CL such that each connected component contains at least one terminals. In addition, for any V in M, a terminal pair S and T exists such that S and T is contained in connected components in neighbor of B. Look at this figure. A set of vertices 6 and 7 is a minimal node merge cut of G and a pair of 1, 4 and a pair of 5, 12. Any vertex in M satisfies the above condition. Next, we define the distance from M to M prime. We adapt the following distance function like this. Here, MCC C prime M is a connected component in G minus M, minimizing the size of C prime minus C. Let M and M prime be a pair of solutions. In this situation, dist M and M prime is equal to 3. For C'1, MCC C'M and M is equal to C1, and the size of C'1 minus C1 is equal to 3. Similarly, for C'2 and C'3, the size of C'2 minus MCC C'2 and M and C'3 minus MCC C'3 and M equal to 0. Next, our goal is to find a closer solution to M prime than M. To this end, we define neighbors as follows. We first consider neighbors which easily find a closer solution. Since M is a minimal node merge cut, there's a vertex B, which is a neighbor of Ci and contained in C'I minus MCC C'I and M. In the bottom of figure, a vertex 7 is a neighbor of C1 and contained in C'I minus MCC C'I M. Thus, by removing vertex 7, the distance function decreases. But M-7 is not node merge cut, since M is minimal. Thus, we have to remove a set of vertices without increasing the value of distance function. In this case, a neighbor of 7 has no terminals, which connect a terminal pair in B. In such situation, by removing a neighbor of 7, we can obtain a node merge cut, and this removal does not increase the distance. Thus, we obtain closer solution. Next, we consider the case which has no such good vertices. In the bottom of this slide, there's a figure, and in this figure, a vertex 6 is not good vertex. Since the vertex 6 is contained in C'I minus MCC C'I and M. However, it is difficult to make M minus 6 a node merge cut without increasing the distance. In this case, we have to choose a set of vertices 6 and 10 in order not to increase the distance. But finding such vertices are difficult. To find such vertices, we enumerate all node merge cut in G minus M minus 6. This problem is the same as original problem. However, this problem can be solved using ST-path separator enumeration algorithm. Thus, we can find a set of vertices which makes M-6 a node merge cut and does not increase the distance. It implies that we can find the closer solution and the supergraph is strongly connected. And moreover, the computation time is bounded by incremental polynomial, since this algorithm does not output same solution. We next consider the special case of node merge cut, node merge way cut. We improve the previous algorithm from incremental polynomial time to polynomial delay. For node merge way cut enumeration, we use the similar strategy of enumeration of node merge cuts. Thus, we give a characterization of minimal node merge way cut. A graph G minus M has connected components C1 to Cl, such that each Ci contains a terminal Ti, and for any V in M, there's a pair of components with satisfying this formula. This is an example of minimal node merge way cut. In this example, any vertex B in M adjacent to at least two connected components in G minus M. By using the previous characterization, we define the distance from M to M prime. We define the distance function as follows, like this. In this distance function, dist M and M prime is equal to 2. Next, we consider how to find the closer solution. Next, we define the neighborhood. The definition of neighborhood is completely same as the case of the minimal node merge cut enumeration. However, in the minimal node merge way cut enumeration, there is no pair of solutions which satisfies the case 2. In the case 2, the difficulty point is moving the terminal vertices. In this problem, each component has at most one terminal. Thus, the case 2 does not occur, and we can find the closure solution only the neighbor of the case 1. Since we can compute case 1 in polynomial time, it runs in polynomial delay. Next, we propose a polynomial delay and polynomial space enumeration of minimal edge multiway cuts. In this algorithm, we achieve a polynomial space enumeration. The key point is a combination of a supergraph technique and the reverse search. We also introduce a similar characterization. A minimal edge multiway cut can be represented by a partition of vertices. Each set of vertices and the partition corresponding to connected components. We use this characterization to define the distance. To reduce the space complexity, we use another technique to design efficient enumeration algorithms. It's called reverse search. This technique is kind of a supergraph approach. In the reverse search, we define one special solution called the root solution. In addition, for each solution, we define one special neighbor called the parent. In the reverse search, we want to build a spanning tree on the set of solutions. By traversing this tree structure, we can enumerate all solutions. Moreover, this structure is tree. It is known that as a technique to traverse this tree in polynomial space. We omit the detail of the reverse search, but the key point are these two conditions. One is any solution M can reach the root by traversing parents, and the parent of M contains M as a neighbor. We define the root solution R as follows. We consider graph G minus T2 to Tk. In this graph, there is a connected component containing T1. We adopt this connected component as C1 in R. We recursively repeat this procedure and we will define the obtained partition as R. In this graph, R is this partition. Next, we define the depth of each solution. The law of depth is similar to the law of the distance and the supergraph technique. We design the depth function and the parent of each solution satisfying the following condition. R has a depth there, and the solution has a depth there if and only if this is R. Moreover, the parent of each solution has a smaller depth than the original solution. To define such depth function and parent relation, ordering of connected component is important. To this end, we define the depth of each solution and the parent of each solution. We adapt the following depth function like this. Intuitively speaking, this value indicates how much the vertex is moved to the right side. We define the parent of M like this. The parent of M is obtained by moving a vertex 10 from C4 to C3. Note that the discussion of the slide ignores some annoying corner cases. However, main concept of the definition of parent are almost same. This operation to compute a parent decreases the depth of solution. Thus, any solution becomes a root solution by applying this operation at most polynomial times. Finally, we consider the neighbor of each solution. In each parent of solution has the original solution as a neighbor. The supergraph makes a spanning tree and we can enumerate polynomial delay and polynomial space by using reverse search. From the definition of parent, by picking a pair of vertex, moving the parent relation and appropriate connected component, we can list the original solution. Moreover, from the definition of a parent operation, each parent has a original solution as a neighbor. Thus, this definition of neighbors makes a supergraph a spanning tree, and we can enumerate polynomial space and polynomial delay. Finally, we prove the hardness result of enumeration of minimal Steiner multicuts. We define a Steiner node multicut. Let T1 to Tk be a set of vertices. A set of vertices M is a Steiner node multicut. If every I is greater than or equal to 1 or less than or equal to k, there is at least one pair of vertices S and T in each Ti, such that S and T contained in this distinct connected component in G minus M. At the bottom of this slide is an example of minimal Steiner node multicut. In this example, this set of vertices disconnect 3 and 9 and disconnect 4 and 5. So this is Steiner node multicut. This enumeration problem is harder than the enumeration of minimal transversals. Efficient enumeration of minimal transversals is a long-standing open problem in the enumeration algorithm area. We consider a hypergraph H and construct a graph G as follows. We make a clique with the size of V vertices and add a pendant vertex in each vertex in the clique. Moreover, each tier is corresponding to each hyperedge in H. To separate at least one pair of vertices in Ti, we have to select at least one vertex in Ti. It corresponds to a minimal transversal of H. Thus, this problem is harder than the enumeration of minimal transversals. Conclusion. We propose 3 efficient enumeration algorithms and prove one hardest result. One is incremental polynomial time algorithm for minimal node multicut, and a polynomial delay algorithm for minimal node multiway cut, and polynomial delay and polynomial space for minimal edge multiway cuts. And finally, we prove that enumeration of minimal Steiner node multicut is harder than enumeration of minimal transversals. As a future work, developing a polynomial delay enumeration algorithm of edge over node multicuts. Thank you for listening.